Hi, we're starting Meteorology B, and we're looking at adiabatic cooling. Now, we know there's different ways to cool things. From earlier in the year, we talked about albedo, that reflectivity off of the surface. So if you hit a white surface versus like an asphalt surface, so concrete versus asphalt, more light's going to be reflected from the asphalt or concrete. Well, the concrete's going to reflect more back because being a dark gray to black asphalt absorbs more energy versus green grass or sandy deserts, so browns. All of those different colors, you remember from the lab we did at the beginning of the year, have a different reflectivity of light in albedo. And so in the winter, if we have a lot of white snow on the ground, a lot of that energy gets reflected back into the atmosphere. That's why in the spring you'll notice that around trees, if we've had a really thick snow cover, the trees actually heat up, melting the snow around it and kind of out from there. And then the more surface of the ground that's exposed, it's a little bit darker than the snow. It absorbs more energy and it keeps melting snow away. So we can actually see that different effect. And one of the reasons why, if we have a year where we don't have a lot of snow on the ground by this point in December, or November, whenever you're watching this, it can be warmer. It's just there's more light that can be absorbed into the surface and it just heats up better. If we have a lot of snow at this time of the year, we tend to start seeing our temperatures stay cooler because more of our energy is being reflected back out into space. So this was a snow cover actually analysis from, no, get this, November 16th, 2014, so a few years ago. But it had a snow event that brought snow all the way down into Texas. And, you know, we're in the Four Corners here. We were getting it in New Mexico, Arizona, Colorado had it. Nevada had snow. Little bits higher elevations in California did. Even in Oregon and Washington. So unless you were like Louisiana, Alabama, Georgia, Florida, Virginia's, Delaware, yeah, and a little bit of Rhode Island. Basically, almost every state in the Union, contiguous Union, had snow that day. And we had a cold front come through right after. Quite often we're going to find, as we look at weather predictions, that right after a big snow event, especially if it's not like a quick, heavy one, but it's kind of long, drawn out, many hours of snow, that's a warm front coming through, and then right behind is often a cold front, not always, but quite often. And you'll notice that if you pay attention during the winter, if we have a snow event, often we plunge into cold right after, and it'll be really clear, no clouds to kind of reflect that, keep that heat in and act as a blanket. Clear and cold, remember? Warm and wet. So low fronts are going to be, we're going to find out, are associated with warm and wet. Or sorry, warm fronts, warm and wet. Cold fronts, cool and clear. So this, looking at it, you should know these are isotherms. You should be able to think that in your head. Okay, a temperature map. These are isotherms. And this was right after that snow event. It was 3 days later. So we actually had kind of a prolonged cold front here. And if you'll notice, Minnesota's in purple, which is down here. And it's between 5 and 10 degrees. We never made double digits that day. It was a cold, cold day. And this is interesting because this is an isobar map, right? We are seeing lines of pressure, and this was as the event was coming through. Here's a really nice warm front. Here's a nice cold front. This is kind of a classic symbol. Here is a low, and you'll notice that this is coming out of the low. So somewhere over here there was probably, well, it's not always perfect. This is a much nicer representation, but we're kind of missing that red warm. Think about this. Red is usually warm, blue is usually cold. Warm is nice kind of rounded edges, so it's a half circle. Cold fronts are pointy triangles in blue. If you're colorblind, then you're gonna have to look for the shape. So anyway, this is a cold front, this is a warm front. We had a cold front come through right after that snow as this low pressure moved past us. And we were plunged into the cold weather. And you'll notice the high pressure was coming in behind it. Over here in the mountains, you were in the 1043, 1034, 1030. Look at all these little highs, and then there's this little low right in between there. But it's higher here, got a little lower, higher here, but they call this a whole lineup of highs. And with that, this is where we start really looking at how are these pressure cells affecting our weather, because they do. Pressure cells helps with pressure as well as temperature. It starts to be an indicator of what's coming in. I can tell you down here it's warmer. This people are having warm air coming at it, and this people right here are still probably warm, and if it's coming this direction, it's a cold front coming right at them. So we know the temperature is going to drop after this nice little warm weather comes through. Interestingly enough, if you're down in Florida, their weather tends to come from Africa because they're in something called the northeast trade winds, where we live in something called the prevailing westerlies. So anything that happens to come out on the Pacific hits like Oregon, Washington, and about 2 days later it goes over the mountains and it hits us. So we kind of look over here to see what's coming at us. Not always, but it's usually a pretty good indicator of what they've had, that mass is coming towards us because of the winds. And this, by the time we're done with this unit, this map will make sense. So we're taking all those isobars we figured out and now applying some weather predictions to it. I don't expect it to make sense now, that's fine. But by the time we're done, it should make more sense. Here's that classic isobar map. And again, we have things called, by the way, on here you're going to see some alternating directions. You're going to see solid blue, you're going to see solid red, alternating directions, and then some purple. There are things called warm fronts and cold fronts, and then there's stationary fronts, and then there's occluded fronts. And they all mean things, and those are the things we're going to be kind of looking at. What does it mean as this pressure cell comes at us? This was the pressure cell for that same day with the temperatures. This was that November 17th, that cold air coming in. And you can see the low pressure's already pushed past and the high pressure's coming at us. And usually that temperature is going to keep dropping until the high comes past us and another low comes in to kind of warm us up. Interestingly enough, a lot of our moisture, now a lot of it does come from here, from the Pacific across with the prevailing westerlies, but we also have a mountain range here and a mountain range here in the Gulf of Mexico. So we actually get moisture coming straight up, and because of that, this is an interesting little thing coming up. As you have the moisture coming up from the south and the other stuff coming in from the west, and if you have just the right conditions, you get that rolling effects. So kind of like that, with the big red spot, remember, it starts to roll. And because you get that shearing, that two different directions, it can start to cause the air to start spinning. And if it goes from vertical to horizontal, that's a tornado. It's a funnel cloud until it touches the ground. Once it touches the ground, it's a tornado. But this conversion of mountains, moisture coming from the south, and our winds coming from here, that's why this is considered Tornado Alley. Just a little precursor. I want to do a really quick review of dew point, because it's going to be a really big indicator for what we're doing with adiabatic cooling.
The air temperature at a given location can vary with many different factors, from the time of day to the color of the surface, the type of terrain, and the geographic origin of the local air mass. The dew point is the temperature below which air can no longer hold water vapor in suspension. It also indicates how much moisture is in the air. The higher the dew point, the more water vapor. As the gap between the temperature and dew point shrinks to within a few degrees, water vapor in the air begins to condense, becoming visible. When the gap closes entirely, if enough moisture is present, it becomes precipitation.
And that's what we're really looking at, because we talked about the fact that we can change temperature by how much sunlight gets reflected back. So on a big snow-covered pack, it's going to be colder than if we didn't have any snow and the sun could get down to the surface, because the browns, the greens, the dark asphalt colors, rocks, all absorb heat much better than snow, which reflects a lot of it back out. So we can have pressure fronts coming in and bringing in colder air from the pole or warmer air from the Gulf. But there's another way in which we can drop our temperature, and that's by going up in elevation. Remember from last semester, we talked about that you've got the the troposphere, and then all the layers above it up to the thermosphere. You've got the, the stratosphere, the mesosphere, the thermosphere. We're really going to be spending the bulk of our time now in the troposphere because that's where weather occurs. But you need to remember from that as we go up through the troposphere, our temperature drops. And our temperature drops at a specific rate due to elevation. And that change in temperature due to elevation is called adiabatic temperature change, which is what we're going to be talking about and doing today in class. There's a very specific rate, but it has two parts. One is when the air is dry, it's not saturated. That's the dry adiabatic rate. The other one is when it reaches the dew point, which is why we're rewatching this video, because once you have water condensing out, it changes and releases heat, and the temperature actually starts to cool slower as you go up because of condensation. So once you reach the dew point, that's called the wet adiabatic rate. Our temperature is going to change, and we're going to change by every 1,000 feet we go into the air. And we can also change, remember I said we can change temperature with pressure, and the lower the pressure, we can change it. And this is...
Well, we're back here. And as you can tell, there's a special feeling in the audience tonight, and that can mean
because
only
Bill
one
Nye's
thing.
there.
It's time to bring on things, water, glasses, electronic apparatus. It's really exciting. What are we going to do tonight?
Well, John, we're going to talk about pressure. We're going to talk about pressure, specifically atmospheric pressure. John, nothing particularly dangerous eye-wise tonight, but you know, it's a great tradition.
What a shame.
It's a
He's going to actually make a cloud.
great tradition, and so I want you to don the safety glasses.
Safety goggles. Great.
And tonight I chose the red. I think this could be my favorite shirt.
Oh,
Because
thank
of the
you.
whole year. I'm not saying. Very cool. John, you look very sharp. Now let's get started right away. Nothing too spectacular. Ordinary deck of cards. I've happened to have selected the Joker.
Oh,
This is a what, John?
it's
Griffin low form.
a
beaker.
test tube.
This is a test tube, right? Now, you
Okay.
may do this in a restaurant with a drinking glass, but at Nye Laboratories, we do it, of course, with the test tube. Everyone's
Oh,
familiar
yes.
with the
Love it.
traditional experiment. Okay, right? Right? You're with me? No applause? That's fine.
That's okay, yeah. You know, that's all right. Only
Okay.
applaud if you feel like it. We're not. Oh,
Esther
okay.
Williams Joker there. So, okay. Now,
That's great.
John, that's fine. Now, what held the card up?
Esther Williams was a actress in the 40s and 50s who was also a swimmer.
A little bit of adhesive that you secretly put on the end of the
John,
chip.
no, John. It was
Oh.
atmospheric pressure, John.
That's right. That's what I meant to say.
Pushing up all around, pushing up all around. Now, what causes atmospheric pressure, John?
The atmosphere.
Well, the atmosphere, but more specifically, gravity, John. Gravity's pulling
Okay.
down all the time on the air and creating pressure here at where is this?
Sea level.
Sea level, very close. John, we put a little water in the great cylinder of science.
Okay.
No need to add a joker, but you can. Then
Okay.
we got to swirl the water, John. You know, whenever we have a
Okay,
cylinder
here
of
you
science, we want to create a vapor in
Okay.
there, a
So
little water vapor.
Swirling the cylinder of science.
Cylinder of science. Now, John,
Okay.
we're going to pressurize it as though we were atmospheric pressure. Then we're going to release the pressure as though we were a cloud at high altitude. See, as the air reaches high altitude and expands, it cools, and water vapor comes out of solution. Now, when it comes out of
Reaches
solution,
the dew point.
it has to nucleate on dust particles, which we'll get from these matches.
So actually when it rains, the water condenses on those particles and kind of cleans the atmosphere. Of course, it makes your cars dirty. If you've ever looked sometimes after a rain, your car, if it was outside, is actually full of dust. And that's because the rain cleared it out of the atmosphere.
And see that little bit of smoke. Now, John, energizing the pump,
No, there is no smoke.
just a tiny.
Just a tiny bit. Oh, you've got to be kidding me. Hang on, we'll find. Okay, so I couldn't find that exact video, but here is Bill Nye doing a cloud demo.
We're going to add some air.
He's already put the
pressurize
smoke
it.
in.
So what happens, you're effectively ever so slightly warming the air inside. And then
Through
that
friction.
warmth will cause the liquid droplets, which are stuck to those particles of smoke, to go back into solution as a vapor. 3, 2, 1.
And if you saw it, it actually condensed into
So
a
not
cloud.
much happened.
So they're going to do it
We're
again,
adding
but
some
now they're going to
dust.
add the dust. So I guess they hadn't added the dust yet.
Similar in principle to the dust you get when wind blows. Blow the matches out and drop them in the bottle. You might figure the smoke you do see is kind or in the plume that's right behind the matches. But watch what happens when we pressurize it,
See, it's kind of,
and then remove the pressure. When we take the pressure off, the air inside will spread out. The molecules will spread out. The energy, the kinetic energy molecules will be spread out, and they will then effectively cool off. When they cool off, the water vapor in there will turn to a liquid and attach itself to the dust of the snow. 3, 2, 1.
there you go. That's a much better cloud. Okay, so here is the end of this part of the notes. You're going to, by the time you get to this video, I'll have another one in there that you're going to watch explaining how we do the math on adiabatic. I did find that Bill Nye video that I showed at the end and put it in after the other one, because apparently that one's just not working. I couldn't find it, but that one is there if you want to watch the video in its entirety.